In this video, we're going to go over electrophilic and nucleophilic aromatic substitution reactions of heterocyclic compounds. So let's begin our discussion with this molecule, pyrrole. Pyrrole is an aromatic compound. It's more nucleophilic than benzene. And so if we perform bromination with pyrrole, we don't need a Lewis acid catalyst like iron 3 bromide. We could just use Br2. Now, where is the bromine atom going to go? Is it going to go on the 2 position or the 3 position? The 2 position is preferred rather than the 3 position. So we're going to replace the hydrogen on carbon 2, or the 2 position. And so the major product will look like this for this reaction. So we're going to put the bromine atom on this carbon. But keep in mind, we're replacing the hydrogen atom that was on that carbon with a bromine atom. This is a substitution reaction. So just keep that in mind. Now let's talk about the relative reactivities of some of these aromatic heterocycles in reference to benzene. So pyrrole is more nucleophilic than furan, which looks like this. It's a 5-membered ring, but with an oxygen instead of a nitrogen atom. And furan is more nucleophilic than thiophene. When you hear the word thio, think of a sulfur atom. And thiophene, which is spelled Thiophene, thiophene is more nucleophilic than the benzene ring. And so towards an EAS reaction, so when you say I write EAS, that means electrophilic aromatic substitution reaction. Now let's discuss why these compounds are arranged the way they are. So these three are more reactive than benzene in an EAS reaction because they can stabilize a positive charge better than benzene can. So once you add an electrophile to any one of these rings, a positive charge will be acquired. And in the case of benzene, we can only put the positive charge on a carbon atom. In the case of these three compounds, we can move the positive charge to the nitrogen or the oxygen atoms. And when you have a positive charge on a carbon atom, even though carbon is less electronegative than those elements, notice that it will be electron deficient. It won't obey the octet rule. And because it doesn't obey the octet rule, this is not a stable situation. Whereas let's say if you put a positive charge on a nitrogen, even though nitrogen is more electronegative, it obeys the octet rule. And therefore, it is better to put a positive charge on these elements rather than carbon because those elements will obey the octet rule, whereas carbon will not. And so that's why they're more reactive in an EAS reaction, because they can stabilize the positive charge better than carbon by obeying the octet rule. Now, in the case of pyrrole and furan, nitrogen is less electronegative than oxygen. As a result, it makes the ring more nucleophilic. Because oxygen is more electronegative than nitrogen, this ring is less nucleophilic than that one. Because electronegative atoms, they can withdraw electron density from the ring by means of the inductive effect. Now, as for thiophene, the sulfur atom is pretty big, and when you're looking at the sulfur atom and the carbon atom, the sulfur atom has a 3p orbital, the carbon atom has a 2p orbital, and so these two orbitals, they don't overlap effectively, making this compound less nucleophilic than these two due to the ineffective overlap of the 3p orbital found on the sulfur atom with the 2p orbital found on the carbon atom. And so that's why thiophene is less reactive than furan, even though sulfur is less electronegative than oxygen. Now let's talk about why the attack occurs at the 2 position rather than the 3 position. So let's start back with pyrrole. And so we're going to react it with an electrophile. So the double bond will break and we're going to add the electrophile on the 2 position. Now let's see what resonance structures we can draw. So keep in mind there's a hydrogen atom here. So here's the hydrogen, here's the electrophile, which means that the positive charge is now on that carbon. Now let's draw the resonance structure by moving the double bond here. And so we're going to get something that looks like this. So we still have the hydrogen and the electrophile, and the positive charge has jumped 2 carbons toward where the double bond was. Now to draw another resonance structure, we can take a lone pair, form a double bond there. And so notice that when the electrophile is added to the 2 position, we have 3 resonance structures as opposed to 2 if it attacks at the 3 position, which I'll show you shortly. Now notice that the positive charge is on the nitrogen atom. And so when that happens, nitrogen still obeys the octet rule, whereas if the positive charge is on the carbon atom, it doesn't satisfy the octet rule. Now the last step in the mechanism is to take off the hydrogen. So let's start with this structure. If we have a base, and if we decide to take off the hydrogen, then the carbon-hydrogen bond will break, regenerating the aromatic ring, giving us basically this compound, but with an electrophile attached to it, if you want to finish the mechanism. You could also finish the mechanism this way. So you could take the base, use it to grab the hydrogen, and then the carbon-hydrogen bond can push 2 electrons here, causing this pi bond to move here, causing these electrons to go back to the nitrogen atom. And so we can draw our final product like this. So here we have the electrophile, and we now have the 2 double bonds here with a lone pair. And so that's another way in which you could finish the mechanism, starting with this resonance form. Now let's see what's going to happen if the electrophile goes on position 3. So here is the electrophile, which means that the positive charge is now on that carbon, which is adjacent to the nitrogen atom. And so the nitrogen atom can use its lone pair to form a pi bond, or a double bond rather. And so now the positive charge is on the nitrogen atom. Notice that we can only draw 2 resonance structures as opposed to 3. And so because we have less resonance structures, we have a less stable situation. Because if you can put a positive charge on 3 atoms as opposed to 2 atoms, it's better to put it on 3 atoms. In this case, we could put the positive charge on 1 nitrogen atom and 1 carbon atom if we put the electrophile at position 3. Whereas if we put it on position 2, we can put the positive charge on 1 nitrogen and 2 carbon atoms. And so this is a better situation. That's why the attack prefers to occur at position 2 as opposed to position 3. Now let's work on some practice problems. So let's use furan as the nucleophile for this reaction. And let's react it with an acid chloride. So here we have the Friedel-Crafts acylation reaction. So what's the major product in this example? So like pyrrole, we have another 5-membered aromatic heterocyclic compound, and so the attack will occur at position 2 in an EAS reaction. So we're just going to replace the hydrogen with the electrophile, which is basically this acyl group. And so the product for this reaction will look like this. So now we have a ketone at position 2. So if you know where the attack will occur, all you need to do is just replace the hydrogen with the appropriate electrophile, and you can easily draw the major product. Let's try another example. So let's go back to pyrrole. And this time we're going to have a methyl group occupying position 2. And so we're going to react this with bromine. Go ahead and predict the major product of this reaction. So what do you think is going to happen in this reaction? Where will the bromine atom go, since position 2 is occupied? And the methyl group is not a good leaving group. We can't just get rid of it like we could with a hydrogen atom. So what are we going to do? Now position 2 exists on both sides, the left side and the right side. So this is position 2, and that could also be considered position 2. So the bromine atom is going to go on position 2 but on the left side. And so that's going to be the product for this reaction. Now let's consider one more example with pyrrole. So what should we do if position 2 on both sides is occupied? Let's use Br2 again. So what do you recommend? What's going to happen here? What's the major product for this reaction? So as we said before, it's very difficult to kick off a methyl group. So we're not going to do that. But instead, we have no choice but to put the bromine atom on position 3. Position 3 is still stabilized by resonance when we add the electrophile. The only difference is we have 2 resonance structures as opposed to 3. So even though the attack prefers to go on position 2, it can still occur on position 3, particularly if we can't put the electrophile on position 2. So then 3 is going to work. Now let's move on to pyridine, a 6-membered aromatic heterocyclic ring. What you need to know is that benzene is more nucleophilic than pyridine. And so in an EAS reaction, in an electrophilic aromatic substitution reaction, benzene is more reactive than pyridine. Now pyridine could still work, but you need to basically add a lot of heat to make it work because it doesn't work well in EAS reactions. So let's react it with bromine. This time, we need the assistance of a Lewis acid catalyst. Also, we need to heat the temperature to a very high degree because this ring is deactivated in an EAS reaction. Now this is position 2, this is position 3, and this is position 4. What we need to know is that position 3 is favored over position 2 and 4. 2 and 4 are not favored. So the electrophile prefers to go on position 3. And so the product of this reaction will look like this. The end result is that we're replacing the hydrogen atom on position 3 with a bromine atom. So this is going to be the product for this reaction. Likewise, let's say if we take pyridine and react it with nitric acid and sulfuric acid. So this is aromatic nitration. Now we need to increase the temperature because room temperature is not enough. And so to get this going, we're going to heat it to 300 degrees Celsius. And so the end result is pretty straightforward. We're going to add an NO2 group to carbon 3. So our final product will look like this. And so that's what you need to know with regards to the electrophilic aromatic substitution reactions with pyridine. Just make sure to put the electrophile on position 3. Now let's understand why position 3 is favored over positions 2 and 4. And so let's react pyridine with a generic electrophile. So putting the electrophile on position 2 gives us this. So we're going to have the positive charge on the nitrogen atom, and we still have these two double bonds and a lone pair. So what do you think we need to do here? What's our next step? So what we need to do is basically take this double bond, move it here to draw the first resonance structure, which will look like this. So now we have a double bond, we have a lone pair still, and then the other double bond is here, but now we have a positive charge on this carbon. And so now we can take this double bond, move it here, giving us this new resonance structure. And now the positive charge is on this carbon. And so these are the 3 different resonance forms that we can draw. Now, which of these 3 resonance forms is the least stable? Is it better to put a positive charge on a carbon atom or on a nitrogen atom? Now, sometimes it's better to put a positive charge on a nitrogen atom because typically it will obey the octet rule, but that's not the case here. Notice that this nitrogen atom doesn't have 8 electrons, it has 6. And so it doesn't obey the octet rule, which is bad. And at the same time, it's not good to put a positive charge on a more electronegative atom. It's better to put a negative charge on an electronegative atom and a positive charge on an electropositive atom. So we have 2 things working against this intermediate. So this is the least stable intermediate. We have an incomplete octet and a positive charge on an electronegative atom, which means that it's not good. Now let's compare it to, let's say, a situation where we have a positive charge on a nitrogen, but we do have a complete octet. So this one, it satisfies the octet requirements, which is good. And so this situation is better than this one, even though the positive charge is on a more electronegative atom. It's because the octet rule is being obeyed. But in a situation where the octet rule is not being obeyed and you have a positive charge on a more electronegative atom, then this situation is the least stable of the 3. So let's call this number 3 for the least stable. This is in the middle, and this is the best situation where the octet rule is being obeyed. So keep that in mind. And that's why position 2 is not good, because we get an intermediate that is not stable. Now the same is true with position 4. If you draw the resonance structures, you're going to get a positive charge on a nitrogen atom with an incomplete octet. But that's not the case if we put the electrophile on position 3. So let's see what's going to happen if we do that. So we need to use this double bond to attack the electrophile. And so we have this intermediate, and the positive charge will be on position 4. So now we could take the lone pair, take this double bond and move it here in that region, giving us this resonance structure. And so now the positive charge is here. Now what do you think we need to do next in order to draw another resonance structure. The best thing to do is to take the double bond and move it here. And so if we do that, notice that we can avoid putting a positive charge on the nitrogen atom. And so looking at these three resonance structures, we don't have a very unstable intermediate. We don't have a nitrogen atom with an incomplete octet. And so because we don't have an unstable resonance structure, position 3 is favored over positions 2 and 4. And so that's why the attack occurs there. Now let's talk about nucleophilic aromatic substitution reactions. Pyridine, which is deactivated towards an EAS reaction, it's activated towards an NAS reaction, a nucleophilic aromatic substitution reaction. Now, in order for this to work, we need a leaving group to be in position 2 or position 4. Position 3 doesn't work very well for these reactions. So we need a leaving group to be at position 2 or position 4. And so if we react this with a nucleophile, let's say like methoxide, the end result is that the leaving group, the chloride ion, will leave. And we're going to replace it with the methoxide ion. And so we're going to get this product. And so that's the basic idea behind the nucleophilic aromatic substitution reactions. You're going to replace a leaving group, if it's a good leaving group, on carbons or positions 2 or 4 with a nucleophile. So now let's go over the mechanism for this reaction. So the first thing that happens is that the nucleophile attacks the carbon that bears the leaving group. And then the pi bond breaks, pushing 2 electrons on the nitrogen atom. And so we're going to get a negative charge on the nitrogen atom, which is good, because it's always good to put a negative charge on an electronegative atom. In addition, nitrogen obeys the octet rule in this example. So this intermediate is stable. Now this intermediate is also stabilized by resonance. The negative charge can delocalize into the ring, and so we can put it on a carbon atom that's 2 atoms away, giving us this structure. And so now we have a double bond here. We still have a lone pair. And now the negative charge is on this carbon. And then we can take this lone pair, form a pi bond, and put the negative charge on that carbon, giving us another resonance structure. And then in the next step, what we can do is basically we can kick out the leaving group. So then we could take this lone pair, form a pi bond, and expel the chloride leaving group, giving us our final product, which looks like this. So we still have the aromatic ring. The aromaticity has been restored. Now we replace the good leaving group with a bad leaving group, which is a stronger nucleophile. And we have our pyridine ring. And so that's the end result of this nucleophilic aromatic substitution reaction with pyridine. So make sure that the leaving group is a good leaving group, and it has to be on positions 2 or 4, and then we can replace it with a strong nucleophile. Now let's consider another example. But this time, we're going to put the leaving group on position 3 as opposed to position 2. Instead of a chlorine atom, let's use a bromine atom. And so let's use methoxide again. So methoxide will attack this carbon, and what do you think is going to happen? Well, we need to push a negative charge on that carbon to begin with. And so we have two groups on this carbon, the OCH3 group and the bromine atom. And so now we have a lone pair on this carbon, and so it carries a negative charge. Now the next thing we could do is draw the resonance structure for this one. So we can take this lone pair, form a pi bond, and push a negative charge on the carbon atom that's 2 atoms away. So now we have a double bond in this region, and we have a lone pair here. So what is our next step after this one? What should we do next? So what we need to do is take this lone pair, form a double bond, and break this double bond, pushing a negative charge on that carbon. And so we have a double bond on the left at the top, and now the lone pair is on position 2. So these are the 3 different resonance structures that we can draw. As you can see, the negative charge never hits the nitrogen atom, and so we don't have a stable resonance structure. And that's why position 3 is not as favorable as position 2 and 4 in this nucleophilic aromatic substitution reaction. Now the last step in the mechanism is to take the lone pair, form a pi bond, and kick out not the methoxy group but the bromine atom because it's a better leaving group. And so our final product should look like this, but it's not going to be this because position 3 is not the right position. So this really shouldn't happen. Let's get rid of that. Now let's work on some example problems. Let's say if we have an OH group on position 2 and a bromine atom on position 4. And we have our pyridine ring. Let's say if we react this with a strong base like methoxide. And let's add some heat to it. What's going to be the major product in this example? So we have a leaving group on positions 2 and 4. So which one will be replaced? Well, we need to determine which group is a better leaving group. Bromide is a better leaving group than hydroxide because hydroxide is a stronger base. The weaker base is usually the better leaving group. So this will prefer to kick out the bromide ion as opposed to the hydroxide ion. So we're just going to replace the good leaving group with the nucleophile. And so the product for this reaction will look like this. And so that's it. Now there's one more thing that I want to talk about for these reactions. Let's say if we have a CH3 group on position 4 or on position 2. The hydrogen atoms on the methyl group, they're relatively acidic. So if we react this with a base, we can deprotonate the hydrogen on the methyl group. And the reason why we can do that is because the carbanion that forms is stabilized by resonance. And so here we have this negative charge that can delocalize into the ring. And ultimately, it can go on the nitrogen with a negative charge. So I can put a negative charge on this carbon, but I'm going to focus on putting it on the nitrogen atom, because that's going to lead to the most stable resonance structure. So here we have an intermediate that looks like this. So as you can see, we have the negative charge on the nitrogen atom, and that makes these hydrogen atoms relatively acidic. So what can we do with this? So let's say we took off the hydrogen from the CH3 group. So we have this right now. This carbon is nucleophilic, and so we can react it with a few things. So let's react it with, for instance, let's say an alkyl halide. We can do that if we want. It'll behave as a typical nucleophile, so we can get a lot of side reactions here. And so just keep that in mind, that these hydrogens are relatively acidic.